It's kind of, it wasn't too hard to follow, I hope. I sort of spliced it together from another class. Okay. It's recording. Let me check the sound level. Testing. Okay. Here we go. Chapter 5. Covalent bonding. We talked about ionic bonding as our starting position because it's the simplest one to theorize. That is, you just need a positive ion or a cation, a negative ion, an anion, and just be sure the charges are balanced. And it sets the precedent for the order of an element that will appear in a formula like that. Positive one always comes first, negative one second. So when we extend this into covalent bonding, we try to use a similar pattern, recognizing that covalent bonding, you don't have ions, okay? But you do have one that's more electronegative than the other. One that draws electrons more closely than the other one does. And it's the second one. It's the one that's in the position of the anion. Okay. I'll point that out as we get to it. That's just an introduction. Okay. So these are the topics, and we're not going to spend time on outline. All right, this is sort of a review, just to bring you up to speed. Ionic bonds always occur between metals and nonmetals. So, and the character of the bond, the ionic character of the bond, is maximum when the metal is as far to the left of periodic table as possible, and the nonmetal far to the right. So our example, sodium chloride, that's virtually 100% ionic. Whereas covalent bonds form between nonmetals. So you just need to know where the metals are and where the nonmetals are in the periodic table. And that, in this one, it's a red line that runs down there like that. And the nonmetals are on this side, the metals are on this side. So it would appear that the possibilities for compounds would be less for covalent compounds than it is for ionic compounds, but that's not the case. Because when you share electrons, the sky is the limit. When you're working with ions, you got this ion and that ion, and occasionally you'll have maybe one metal ion that could be 2 or maybe 3 possible charges, right? So you're limited there in absolute charge. But when you're talking about sharing electrons, the sky is the limit, right? For example, you can have compounds of nitrogen and oxygen like this. Just keep going. And these are all covalently bound compounds. And living systems take advantage of that. All the important molecules in your body are covalent molecules, like carbohydrates, proteins, nucleic acids, and fats. Those are the 4 basic types that make up the body. And then you insert ions into this system to do certain things. But the matrix of your body is covalent. Okay. Just to repeat, the difference, of course, is that ionic bonds form between complete ions, a complete transfer of electrons to one or the other, and you get a separation of charge, full charge. And by that I mean the presence or absence of an excess of electrons. You got more electrons than protons, you got a negative charge. You got more protons than electrons, you get a positive charge. Whereas with covalent bonds, the electrons they might spend a little more time on one side of the bond than another, but they never completely reside around the other atom. The nature of ionic compounds is such that they do not produce discrete molecules. So when we write this sodium chloride, that's the simplest whole number ratio of sodium ions to chloride ions. Right? That's not a molecule like that. It's actually, I think I drew this before, it's actually a network of positive and negative ions. Okay. But the simplest ratio is for every one of these, there's one of those. But when we write a covalent compound, we are implying discrete molecules, like water, that stands by itself. The only time that it forms a solid, say, like an ionic compound, nearly all ionic compounds are solids. The structure of the solid water, ice, is not a network of ions. It's an association of water molecules. Right? And in fact, the association of water molecules in ice is rather unique because as they form a solid, they distribute themselves in a hexagonal shape. Right? That's why snowflakes have 6 sides. That's a reflection of their internal structure. But molecules are discrete. They interact with one another, but on a different level than ionic compounds. Whereas ionic compounds at room temperature, they're all solids. Of course, if you get them hot enough, they'll melt, right? But you get them really hot. Covalent compounds can be any one of the phases, solids, liquids, or gases. When you dissolve an ionic compound in water, it breaks apart into its individual ions, and now it will conduct electricity. It has a mobile charge in it. The solid ionic compound will not conduct because those ions are locked in place. They cannot move. And they don't turn their electrons loose to move either, not like a metal does. Whereas a covalent compound could go either way. Some covalent compounds do not dissociate in water, right? So they do not conduct electricity. They're non-electrolytes. Whereas soluble ionic compounds are electrolytes. But there are some covalent compounds that do dissociate, most of them just partially, and produce some mobile ions, like weak acids, like acetic acid. If you put enough acetic acid in solution, vinegar, then it'll conduct electricity. Let's see, how will you a paper? I think I've got one in here for you. Somewhere. Of course, it's going to be on the bottom.
I'm not afraid of more paper sticks.
Here we go.
Thank you.
Do you have a copy of today's lab? Anybody else need one? Separating binary mixtures. I handed it out last week, so if you want it. Yeah, you got it.
The one I emailed to you?
You emailed one too? And you haven't got it back yet? Okay. When did you email it?
Day after I took, morning after I took it to him.
Oh.
Sunday.
Okay. I'll check after the lab time rolls around.
Staple, that's all.
This is not the one you emailed, though. Is this the one you emailed? Oh, okay. That's better. All right. So, all right, those are characteristics, actually kind of a comparison of ionic and covalent compounds. On the way to talking in more detail about the covalent bond model. So these two atoms will bond with one another if there is an incentive, chemical incentive to share electrons. Then they would form a covalent bond. So we need to look at first the nature of the bond, and then what's the driving force for forming the bond. All right, so here's an example of the simplest covalent molecule. Just two hydrogen atoms come together. And we know that hydrogen has one proton. Right? That's what makes it hydrogen. And the most abundant isotope has no neutrons. So we're going to focus on that one. And then, of course, it has one electron to balance the charge. Well, if we write that, if we just put one dot up here for that electron, then it's easier to visualize rather than having to draw this model. Right, so we have two of these hydrogen atoms. And let's see, I'm trying to remember what we have covered in this class and what we haven't. Because I don't want to throw something at you. Atomic structure. Okay. We have talked about it yet. Okay, so we have in this first shell, right, we can only have two electrons, the 1s shell. Like that for each one. And remember, this one can hold two electrons only. So what they want to do, this shell will be satisfied if we can put two electrons in it. But the way sharing works is, it's just what the atom thinks it has, in quotes, because atoms can't think, of course. But if we can get this one to think that it has two electrons, and that one to think that it has two electrons, that they're both happy. And they do it by sharing. So they come close enough. Now they have two between them. This one thinks it has two, and this one thinks it has two. So that shell is full. And in fact, it looks like, to the atom, that it's, electronically speaking, helium. Because helium is a noble gas with two electrons in its first orbital. That's why the noble gases don't react. Because their outer shells are filled. They don't need any more electrons. And they're not going to give any away either. Right? So noble gases don't play with anybody. Whereas the others are trying to get to the noble gas configuration. Right? For hydrogen, it's only two electrons that it needs. So once it forms a bond with another hydrogen, it's satisfied, game over, bond is formed. The other way to look at it is the energy level, the amount of energy, the energy level. Let's do it this way. Right? So here's the energy, and here's one of our hydrogen atoms. Here's another hydrogen atom, and this one is at that level of energy. This one's at this level of energy, right? So as they get closer together, and this is distance, okay? As they get closer together, the energy levels drop. Till they get down lower, right? And at that point, you have the molecule, the bond is formed. So the stability is supplied by decreasing the overall energy. They're seeking the lowest level. It's kind of like when you pour water under the ground, you can find out where the lowest spot is, right? Because it will run to it. That's what these guys are doing. They're decreasing their energy levels to a point where they're at a minimum. Minimum energy means more stable. And stable means a strong bond. So in order to break that bond, you've got to add the energy difference between here and here. Right? So if we add energy back in there, we can bust them apart. Okay, any questions? Okay, so the use of dots is called Lewis dot notation. Okay, did we go over that already? Okay. And for hydrogen, actually hydrogen is the only one where we have two dots, and that's it. It satisfies the duad. That's for hydrogen only. Everybody else is the octet. So the octet includes an s orbital and a p orbital, because you can have 2 here and 6 here. That's why it's an octet. Now, it might be in the second period, could be in the third period, but that's where most of our activity will be with octets, in the second and third period. We might jump into the fourth occasionally, but things start getting complicated when you get down in this region where these d orbitals kick in. Right? So the octet is fairly reliable for this period and that period right there. And we show shared electrons between the atoms. That means they have formed a bond. Now, the notation that I prefer is whenever you have a bond like that, I use a line, and a line means 2 electrons. Okay. And if you have any unbound electrons, then you put those as individual dots. Okay. Oh, just check. A covalent bond occurs when there's a sharing of valence electrons between similar or identical atoms. Identical atoms, example, are the dihydrogen. Any of the diatomic elements, if you look on the periodic table, the diatomics are hydrogen. At room temperature and normal atmospheric pressure, these elements always exist as diatomics. That is, 2 of the same atom bound together. Hydrogen's 1, nitrogen, oxygen, fluorine, chlorine, and bromine. They're all diatomic. So if you encounter a word problem that says chlorine gas reacts with something, you better write it like that. Otherwise, your equation will not balance. So you need to know the diatomics. That's why in that first handout I gave you a periodic table, I identified the diatomics with, I think, the little blue squares. Oops, what happened? I must hit the. Okay. Oh, wait a minute. Or it could be between similar atoms. What that means is, actually, that's not complete. Similar nonmetals. If they're similar metals, then you have a different type of bond that we're not going to discuss here, the metallic bond, right? That takes a little more than we've got going for us in this course. So we just subdivide our bonds into ionic and covalent and let it go with that. We need a more advanced model to understand metals. Okay. So we can subdivide the electrons in a molecule, a covalently bound molecule, in terms of which ones are bonding and which ones are non-bonding. So the bonding electrons are the ones that are shared. Right? So these are bonding, 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 that line. And a line always represents 2. So if you have 2 lines, that means 4 electrons, or a double bond. If you have 3, like with dinitrogen, you have 2, 4, 6 electrons between the nitrogens, and you have an unbonding pair here, or a non-bonding here, and a non-bonding there. Okay? And if you count them up, 2, 4, 6, 8, that nitrogen thinks it has an octet. 2, 4, 6, 8. That one thinks it has an octet. And the triple bond is naturally stronger than the double, which is stronger than the single bond. That's why nitrogen gas in the atmosphere stays that way. And it's considered relatively inert. Right? We can, by chemical means, break that apart. You know, maybe combine it with hydrogen and make ammonia. Right? That's what Fritz Haber did just before World War I, to make ammonia and then nitrates for Germany so they could make their explosives. Or if you're a legume, a plant, you know, like clover or alfalfa, and you have these little symbiotic organisms in your roots, they can take nitrogen gas from the air and convert it into fixed nitrogen, we call it, into ammonia first and then nitrates. And then the plant can use it. That's why it takes less nitrogen fertilizer for a legume than it does for a non-legume like corn or Bermuda grass or something like that. But it's a very, very strong bond. In fact, when you open a bag of potato chips, the reason they're poofy is they've been flushed with nitrogen in the packaging process. What that does is it expels all the oxygen from the bag. The oxygen is what causes rancidity in the oil that's in your potato chips. So that way they don't have to add an artificial preservative. When I was growing up, they used to put things like BHA and BHT in there, which would scavenge oxygen. But there was some evidence that those chemicals over long-term exposure were hazardous. So they gradually phased them out and converted to just flushing their bags with nitrogen. They got rid of the oxygen and problem solved. And nitrogen is not a greenhouse gas. So all the greenhouse hysterics were happy too. Oh, they tried CO2 because it does the same thing. But, you know, that puts all the lefties up in arms. Okay, what's the difference between bonding electrons and lone electron pairs? Well, this is kind of a repeat of what I just said. The bonding ones are the ones that are between the atoms that form the bonds. And the lone electron pairs are non-bonding. And we only specify in our model the valence electrons, right? So the valence electrons would be positioned around the atom. Say if this one's not bonded, it would have 5, like that. 5 electrons around the nitrogen atom are the valence electrons. Now that's not all the electrons in nitrogen, right? Because we know that with 7 protons, it has 7 electrons. We're only accounting for the valence electrons. The other 2 are the core electrons, right? And they're not involved in bonding in any way. So we don't note them in this Lewis model, okay? So just a word of warning, don't get confused. If you see something up there and say, wait a minute, that's not all the electrons. Well, it's on purpose. We're only interested in the ones that are available for bonding. We don't have to use all of them, right? But some of them bond, some of them don't, but they are all valence electrons. Okay, let's see. So that's what a single bond looks like. 2 electrons between the atoms, designated by a line. Here's carbon dioxide, right? So you've got 2 pairs here, 4 there and 4 there. But we're not showing any non-bonding pairs, right? So if we rewrite this correctly, 2, 4, 6, 8, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. That would be the proper structure with all the electrons accounted for. Okay? And each one sees that it has an octet. And then the triple bond, I've already showed you that one. Okay, just a reality check. In a double bond, how many electrons are shared? 2 times 2 is 4.
I don't know, I was thinking 8, 6 more likely. Yeah, all this talking octets. Yeah.
Octet stuck in your brain.
Yeah.
Okay. Most non-metallic elements, that is, these guys over here, they have a strong tendency to form a specific number of covalent bonds. And that's helpful when you start writing structures. If you see a nitrogen atom in a structure, you're saying, okay, that puppy's going to have 3 bonds to somewhere, right? If it has it to another nitrogen atom, got them all accounted for. But what if we only have hydrogens around it, right? And hydrogen can only have 1 bond each, right? Because it's only got 1 electron to share. So 1 bond is the maximum. It can't have any more. So if you put hydrogens around here, you can only have 1 each. But nitrogen still has 3 bonds, right? So, and the families are similar. Phosphorus is the same way. Oxygen tends to have 2 bonds. Yeah, just reality check. 2 bonds for oxygen. So if we have oxygen by itself, it's going to be like that, well, without the lone pairs. But if we have oxygen bound to something else, like hydrogen, it's still going to have 2 bonds, but the hydrogen can only have 1. So oxygen, water, 2 bonds for oxygen. Carbon can have 4. So if we bond carbon to carbon, we'll have and then it just keeps going on forever. So what do we have there? Diamond. Diamond is a tetrahedral network of carbon atoms. So it's like it's one massive molecule. If you have a diamond on your finger that has no flaws in it, it is one single molecule. In other words, if you were small enough, you could hop from carbon, step on the bond, go to the next carbon, and never, your foot would never be in open space, all the way from one side of the diamond to the other. There's no breaks. Of course, it's hard to find those. Try as I would, I couldn't find one cheap enough that I could afford for my wife's engagement ring. So I found one with a little tiny flaw. We stuck it under the post. Okay. The number of bonds formed is equal to the number of electrons that the non-metal atom must share to obtain an octet. Okay, so if we look at that, how many electrons does nitrogen need to make it to neon? 1, 2, 3. 3 bonds. Carbon, 1, 2, 3, 4. Or oxygen, 1, 2. Or fluorine, 1. So how many electrons does it need? That's the same number of bonds. Now, when you get over on this side, you're too close to that metal-non-metal boundary for boron to obey that rule. 1, 2, 3, 4, 5. Boron doesn't make 5 bonds. Boron's more likely to make 3 bonds because it goes backwards. It goes 1, 2, 3.
Less work.
Mm-hmm. Exactly. Okay. So this is what 2 single bonds would look like for oxygen, or 1 double bond. Satisfies conditions. Either way, you still have an octet for oxygen. Nitrogen, we can form it this way. With our ammonia, put hydrogens here. Or this one, you could put an oxygen there. That would satisfy oxygen with one side of nitrogen. And then you could stick a hydrogen out here. Okay? Or you could put another nitrogen over here. Or in some cases, you can put, well, let's not go there. That would muddy the waters. Let's keep it simple for now. Carbon, of course, can form 4 bonds in multiple possible arrangements. So, and this is kind of gives you a clue as to why carbon was chosen as the core of organic structures and biochemical makeup, because it has such versatility in its bonding matrix. You can form, well, living systems form just massive varieties of compounds based on carbon structure. And organic chemists have taken it to extremes, to the point now that when I was a kid, most everything in your house was engineered from natural materials. Okay? You just break them down and put them back together. Now, I would dare say that half or more of everything in your house is constructed from the molecular level up. Lots of them plastics, right? Or polymers of some kind. So we're engineering our world at the molecular level. And a lot of it is based on carbon as the backbone. And we interject other elements as needed to modify the structure. Okay, how many covalent bonds can oxygen form? 1, 2. Right. 2 moves to the right, you got neon. Okay. Now I'm going to throw this one at you. I hope it sticks. It's a little concept change. What we've been talking about up to this point is when two atoms come together, they each contribute something to the bond. One electron from one from the other, maybe two from one from the other, whatever it takes. But there are certain classes of covalent compounds that are formed by electrons being shared from one atom with no contribution from the other atom. They're still shared. It's not a complete transfer. So you get electrons being donated from one atom into the bond. And then it's kind of like a parasite. You know, this guy doesn't give you anything, but he gets a bond out of it. This guy gives everything, but he gets a bond out of it. That's called a coordinate covalent bond. So, and there has to be an advantage to it. I mean, you have to think, bonds don't form by accident. There has to be a driving force. In other words, the energy level of the reactants before has to be higher than the energy level of the product after. That's the basic driving force. You're going to a minimum energy level, more stability. So there has to be a driving force that would impel one atom to give up two electrons into a bond, whereas the other one does not. And what this allows that atom to do is to form a bond with non-bonding electrons from another atom. So here's an example. So this molecule is, let's see, how would I write that? HClO would be the way you write this one, even though oxygen's in the middle. I probably ought to write it this way, just so it's not confusing. HOCl. And what it wants to do is form a bond with oxygen, because, well, this one's already got, right, 2, 4, 6, 8, it's already got an octet, right? So it should be happy. But this one over here doesn't have an octet, right? So it's going to induce that one to give up its electron to form a bond. So these both electrons are contributed to that bond, and now we have HO2Cl or HOClO. Now, this one still has its octet, but this one also has an octet. That's a coordinate covalent bond. Now, if you encounter this compound, independent of the reaction that was performed to produce it, you can't tell that that was formed by coordinate covalent bonding. There's no way to tell. You have to study it in the reaction form to know that its origin was covalent, coordinate covalent. Right? You can't. There's no way to tell just in a state, sitting there by itself, that that's what happened. It's all in the process. Okay. I'm not going to spend a lot of time on that. I think we've already beaten that one enough. Let's restate what I just said. Nitrous oxide. Let's see. Okay, this is a good point. The first point I've already made. They're indistinguishable from any other covalent bonds. Can't tell them apart. except to note, in some cases, like this one, nitrous oxide, like laughing gas. Except to note that in this case, nitrogen normally forms 3 bonds, right? Right here, 1, 2, 3. We said that before, right? As if it were a hard and fast rule. Of course, rules are made to be broken, right? In chemistry, it works in chemistry just like in traffic laws. But with something like this, you still have these 2 lone pairs that are available for bonding if they can be induced to do so. So if we approach it with another one of those oxygens, right? So this one donates both electrons, and we form a bond there. Now we've got nitrogen with 4, this nitrogen with 4 bonds, that one with only 3. But they both still have their octets. And that happens by coordinate covalent bonding. Carbon monoxide is another example. Right? Instead of having another oxygen on this side, all we've done is taken that oxygen away and kept those 2 bonding electrons for that carbon. Now in this case, carbon does have 2, 4, 6, 8 valence electrons, but it doesn't have 4 bonds. It's got its octet, but it only has 3 bonds. And I think the toxicity of carbon monoxide as opposed to carbon dioxide and its competitive inhibition of hemoglobin, oxyhemoglobin formation. Somebody had AMP in it? No. Okay. The body transfers oxygen from your lungs to your tissues by bonding it to hemoglobin. Actually, it's the iron atom in the hemoglobin. Each hemoglobin molecule has 4 iron atoms, and each iron atom can take 1 oxygen. Okay. So normally, the partial pressure in your lungs is high enough so that it outcompetes anything else, and it attaches to the hemoglobin, delivered to your tissues, and you live. The problem is, if you're exposed to enough carbon monoxide, the attraction of carbon monoxide to hemoglobin is much, much higher. And once it attaches to the iron, it doesn't let go. So it competitively inhibits the absorption of oxygen in hemoglobin, and you suffocate at the cellular level. Okay? And I think it's because of this pair right here that wants to bond. Okay. When does a coordinate covalent bond form? When both electrons of a shared pair come from one of the 2 atoms. That's definition. Okay. Now, did we go through these steps, how to write Lewis structures, or did I promise to do it?
I was looking at them, they seem real familiar.
Okay. So we'll not labor this one, we just sort of review. So rather than go through each one of these steps, let's just take an example. Let's take, let's see. Well, we'll take a simple one, like a HF. Okay. We have this compound given to us. We want to write a Lewis structure. So the first thing you do is count up all the valence electrons. Right? Hydrogen's got 1. How many does fluorine have? We'll look from the left. 1, 2, 3, 4, 5, 6, 7. 7 valence electrons. So that means we have 8 electrons total. We have to distribute in our Lewis structure. Right? So what you do is, first, you establish a single bond. between the two. In this case, fortunately, we only have 2. So that's 2 electrons accounted for. We have 6 left that we have to place. Whenever you have a hydrogen, there's no more room, right? Hydrogen can only have 2. It's already got 2. So the other 6, 1, 2, 3, 4, 5, 6. We're good. We're done. Because hydrogen has a duet, fluorine has an octet. As long as those conditions prevail, then you're done. If you get to this point and you still don't have an octet, then we've got to move electrons around to make sure everyone has an octet. And as luck would have it, there are exceptions. Hopefully I can show you 1 or 2. Okay. Ammonia is a good one. So let's do ammonia. There we go. So how many do we have for hydrogens? 3. Nitrogens? 5. That one counts too. So we have 8 electrons. Okay. Nitrogen is going to be in the center. It has to be, because 2 hydrogens can't bond to each other and bond to nitrogen too. So this one's easy. Nitrogen has to be the central atom. So we form a bond with each one of them. There we go. 2, 4, 6. So 2 electrons left over. Can't put any more on the hydrogens. And as you start placing the excess electrons in a model, you start from the outside and work your way in toward the center. But since the hydrogens have all they can handle, we're left with nitrogen to accept the last 2 electrons. Okay? And that would be a Lewis structure, because duet, 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 2, 4, 6, 8 octet. How about carbon tetrachloride? So carbon has 4. Chlorine has 7 each, which is 28. So we have 32 electrons. Carbon's going to be in the middle, with chlorines around it. And when you're first drawing a Lewis structure, it's okay to arrange things on a flat screen, because we're not interested in geometry yet. You get the Lewis structure first, then you deal with the geometry. Okay, so we've got 2, 4, 6, 8, 24 electrons left. Okay? So notice we've got 1, 2, 3, 4 chlorines and 24 electrons. So if we put 6 around each one, we're done. Right? And that's 2, 4, 6, 8. That's an octet. There's your Lewis structure. And we have an octet here, we have an octet there. Everybody's got an octet. Okay. Which is the total number of dots in the Lewis structure of SO2? For this one, all you have to do is just say, first, well, you do have to draw the structure, because it says the total number of dots. And I assume what they're saying there is non-bonding electrons, because dashes would be bonding. Right? So sulfur is same as oxygen, 6. So we have 12 here, 18 total. So we have sulfur in the middle, oxygen, oxygen, minus 4, right? 2, 4, 16. Then we work our way in. So normally what you do, is work your way around in a circle, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 4 electrons. 4 electrons we haven't used yet. And oxygen's got an octet already. Okay? But sulfur doesn't. Since oxygen's full and we're working our way in, these other 4 need to go on that sulfur. 1, 2, 4. So we're all done. Now the question is, how many dots do we have? 2, 4, 6, 8, 10, 12, 14, 16. Wait a minute. 2, 4, 6, 8, 10, 12, 14, 16. That's wrong. Unless I counted wrong. Did I count wrong? Sulfur and oxygen. Oxygen 6, 3 times 6 is 18. Okay. 2, 4. Ah, I did miscount. 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, so they're counting dashes as dots. Okay, here's the problem. If I did that right. Minus 2, 4, 14. Yeah, that's my mistake. 14. Minus 12. 2 here. Okay, now what we got is a problem of octets for sulfur. Okay. Taking into account the fact that they're counting all these as dots. Okay, I think that's why it's 18 here. And it's total number of 18 there. But if we're going to finish this Lewis dot structure, sulfur needs an octet if we can get it for it. So how do we do an octet for sulfur? Well, if we make another bond, 2, 4, 6, if we make another bond with maybe 2 of these, say put these down or put these over here into a bond, then we still got 2, 4, 6, 8 for that oxygen. And now we have 2, 4, 6, 8 for the sulfur.
Okay, so it would be one of those, I've already forgotten its name, the one we just learned about. Yeah, the coordinate. It'd be one of those coordinate ones, right? Because it's sharing, but it's not really giving.
Yeah, not strictly speaking, though. The reason being is this is an artificial construct.
Yeah.
This is not the actual bonding process. Because we could just as easily have put these 2 electrons over here first and then moved them over.
So it's a labeling thing.
Yeah.
More or less, not strictly how it bonds. Okay.
Right. So now if we do it that way, it looks like this. Okay, now we have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. But notice, what if instead of going like that, we did this side? Because these are unique atoms, right? So this structure is just as valid. Okay? So either one of these is a valid Lewis dot structure for sulfur dioxide. So what do we do when we report our structure? Well, we have to use a cheap trick called resonance. So we set this one up. Actually, we put it over here. this, and we say it bounces back and forth between them. We don't know which one is true. So just, it resonates between the two. In reality, these two bonds right here are equal. Now, the way we've got them drawn, this is drawn as a single bond, and this one has a double bond. And usually, double bonds are shorter than single bonds because they're stronger or tighter. Triple bonds are even stronger than that. So this one should be a shorter bond than that one, the way we've drawn it. But it's not. They're both equal. Right? So in reality, what you're looking at is a partial double bond on either side. And then that gets messy. So you can't do that with Lewis dot structures.
I was going to say, if it's only a partial on both sides, when it means only taking one electron per both.
Yeah, it kind of distributes. So these theories and these models all have play feet, right? You just have to recognize where they are. This has its value. You can use this in certain circumstances. You just have to learn when you can't use it, or what to do on a test. Just spit this back out.
On a test, put that. Got it.
Yeah.
That's all I need to know. My poor notebook looks like I've just scribbled in it.
Okay. Now, here's kind of a hybrid situation. When we have ionic compounds that we mentioned last week that are formed between cations and anions, and one of them might be polyatomic. Remember the polyatomics, like sulfate. Right? They behave as a single unit. So this will be an ion bound to some other cation. Could be a metal ion. It could be the one other polyatomic that's positive, like ammonia. Right? In which case, you need two of these, right? Now we're going to look at the internal workings of the polyatomic. The polyatomics exist and behave as a single unit because they are all covalently bound ions. So that sulfate ion is a covalent unit with a charge. Okay? So here's what a sulfate looks like, and here's how you draw it, right? We can't say that the charge here is localized on any one of these atoms. It's characteristic of the whole. So you put brackets around it and put the charge outside. You're not saying that the charge is anywhere in particular. We can't say that this is the structure because this implies that potassium sulfate is itself a covalent compound, which it's not. It's an ionic compound. It just has this covalent polyatomic ion built into it. So this is the correct structure for an ionic compound built from polyatomics. Okay, how many valence electrons are present in polyatomic ion? Well, we showed it on the previous one, but let's count them up anyway. Okay, so for that ion, how many valence electrons? Well, sulfur and oxygen are in the same family, so they have the same number, right? 6? 6 each?
Yeah.
6 there, 6 there. So we have 5 times 6 equals 30, but we've got 2 extras. This is for the neutral, right? This is extra. So there are 32 valence electrons in that ion. So don't forget to count these. Okay?
I'm trying to figure out how I ended up with 36. I guess I counted them.
The same way I did. You just counted wrong.
Just counted.
Yeah.
I was trying to count it real quick on my own, and it was just.
So let's see if they're all accounted for. There should be 32 of them, right? 2, 4, 6, 8 in the bond. And then looks like there's 6 around each one of these. So that's 24 plus 8 is 32.
Yeah.
Right? And at this point, when you write this structure, that charge is a consequence of all of these electrons. It's not separate electrons up here. Now, when you write it this way, you're saying that there are valence electrons here, here, plus these 2 extra electrons. When you write it that way. When you write it this way, you're putting all of those electrons, including these 2, into that structure. And this says that with those electrons positioned the way they are, they give you a net -2- charge. It's redundant. -2-. Okay. Now, what do we do with geometry? Throw our hands up and go home? No. There's a method. It's important to know the 3-dimensional structure of a molecule in order to know how it's going to behave in contact with other molecules. Right? And in particular, I'm talking about polarity. Right? Does it behave as if it has a pole to it? You know, like a magnet, north-south pole. So magnets with the north pole repel, and if you put the south pole to a north pole, it attracts. Similarly with molecules, if they have a polarity to them, if they have a slight imbalance in electron distribution, one side of the molecule being slightly negative and one side being slightly positive, not complete ions, just a slight imbalance, then that gives them the potential to attract the opposite pole of another molecule. Okay? So the way to know that is, first of all, answer the question is, are the bonds polar? Each one of the bonds in the molecule can have a polarity of its own, like a slight distribution, even though they're shared, distribution of electrons toward one atom more often than toward the other. Then, what's the geometry? The reason we need to consider geometry is if all the bonds in the atom are polar, but they're symmetrically positioned in a geometric pattern so that they cancel one another out, then the overall molecule is nonpolar. Okay? Perfect example of that is carbon tetrachloride. So think of this down here as a triangular base. Okay? And then this forms a tetrahedron, a regular tetrahedral shape. Right? Chlorine draws electrons more strongly to itself than it does to carbon. So we're going to have a slight movement of electrons toward each of the chlorines. Right? And we use this symbol with a plus sign and an arrow to show which way the electrons prefer to move. Right? So that gives us a slight negative charge, and I'll use this small Greek delta to mean that it's not a full charge, just a slight distribution shift. And each one of these has a slight negative. That makes the carbon slightly positive. Actually, to balance our math, it would be like this. But because all of these, we call them dipoles. All of these dipoles are positioned regularly around the tetrahedron, they cancel one another out. So even though the bonds are polar, the molecule is nonpolar because they're pulling equally to the corners of the tetrahedron. That's why carbon tetrachloride was such an effective dry cleaning agent, right? Because most of the soil in your clothes is oily based, and it doesn't damage the fabrics, you know, like harsh detergents would. So the first dry cleaning, actually the industry started with carbon tetrachloride, and it wasn't until OSHA and the EPA got hold of it and said, gotta get rid of that stuff. It's making your workers sick. But it was very effective at dissolving fats because fats are nonpolar. The solvent's nonpolar. Like dissolves like. You've heard that before. Like dissolves like. Water-soluble stuff. Water's polar, so polar things will dissolve in water. Non-polar things. That's why soaps work. Soaps bridge the gap. Soap is a molecule that has a polar end. If the molecule is big enough, you can have polar on one end and non-polar on the other. And that's what a soap does, or a detergent. So part of it dissolves in water, polar end, and the non-polar end dissolves in the oil. And that way you suspend the oil and strip it from your clothes. You're good to go. Okay, so you need to know these two things. Are the bonds polar, and what's the geometry? And to do that, we have a model, this theory. VSEPR stands for valence shell electron pair repulsion, which is a long, complicated word, but all it means is the electrons that are positioned in your molecule try to get as far away from each other as possible. Okay, they try to position in a regular pattern, if possible, away from each other because electrons repel. And these, we only consider the valence shell electrons. They can either be in bonds or lone pairs, right? And what this does is it minimizes the repulsive effects. The farther apart they are, the less push there is. And that's a more stable position. Okay, so how do we do that? Well, first you have to draw the Lewis dot structure. You got to find out where all of your electrons are located, either in bonds or lone pairs. Okay? And then you count up the number of groups around a central atom, right? So this geometry is based upon the central atom. So what's an example? Well, we've already drawn ammonia, right? So if we just draw ammonia the way we did it before, this, that, okay, how many groups are around nitrogen? 4, right? So when you have 4 groups, that translates into a regular structure called a tetrahedron. Right? So if we draw this geometrically speaking, we would say nitrogen's in the middle, and then we have a lone pair up here, and we have hydrogen back there in the back, and then we have a hydrogen here, we have a hydrogen here. So this forms the base of our tetrahedron, and this forms the apex. Okay? Try to visualize that. Okay. So now this is, in this case, since we have 4 groups, it's a tetrahedron. This is the electronic geometry. This takes into account all bonding and non-bonding electrons. You have to do that first to establish its electronic geometry. Now, if you want the molecular geometry, where you're only interested in the atoms that are bonded, then you just cover up the lone pairs and say, what do we have left? What do we have left? Looks like a pyramid, doesn't it? Except this is not a square-based pyramid like the Egyptians. This is a trigonal pyramid, a triangular base. So the molecular geometry in this case is a trigonal pyramid. Now, what does that mean? That means that the geometry, the dipoles that are being marked here, they generally go toward the nitrogen, are not symmetrical. Plus, we have this lone pair. So what we have is we've got a distribution of slight electrical charge that direction. And on this end, a collection of positives. So ammonia is polar. It's a polar molecule due to its geometry. Oh, and the polar nature of the bonds with the lone pairs. Okay. Did I lose anybody? I'm trying to keep it as simple as possible because it can get really complex. So these are the steps that you would use. You first, of course, draw your Lewis structure. Right? You got to know where everything is to start with. This is not geometric, but this is all of our electrons are accounted for. Then you count the number of groups around the central atom. 1, 2, 3, 4 in this case. If there are any double bonds here, they count as one group. Triple bonds, one group. Right? So if we were to discuss this one, around this nitrogen would be 2 groups. Around this nitrogen would be 2 groups. So the geometry around each nitrogen is identical. And when you have 2 groups, you have a linear structure. Okay? But since they're identical, there's no dipole between them. So the bond is not polar to begin with, so the geometry doesn't matter. If none of the bonds are polar, then the molecule is going to be nonpolar. Nonpolar bonds, nonpolar molecule, doesn't matter the geometry. But if you have polar bonds, then the geometry will tell you whether the molecule is polar or nonpolar. Then you establish the electronic structure, whatever it happens to be, and then you cover up the non-bonding pairs and establish the molecular structure. Okay? So for water, we draw water. Our Lewis structure might look like this. Okay? 2, 4, 6, 8, 2, 2. Okay? We have 4 groups, so it should be in the form of a tetrahedron electronic structure. So we would have maybe we have a pair back here. Then we would have a hydrogen here, a pair up here. And so that forms our trigonal base. There's our tetrahedron. Then if we cover up the lone pairs, what we have is a bent molecule, like that. And the dipole for each of the bonds is toward the oxygen. So since they don't cancel one another out, plus you got those lone pairs toward that side, oxygen is a very polar molecule. So if you have pure water, oxygen is going to be like this. Like that. And when they line up in pure water, the oxygen from this one's going to line up with the hydrogen of that one and form a weaker bond. It's not as strong as a covalent, but there is attraction there. Right? So that's why water is liquid at 1 atmosphere pressure and 20 degrees centigrade. If it weren't for this fact, water would be a gas, and we'd all be in big trouble. So, thank your lucky stars or whoever you want that water is polar. Okay. So let me see. Get my bearings here. We're okay on time, I think. All right. So I'm going to give you a list in a couple minutes of the number of groups that you count in your Lewis structure and the electronic structure that goes with them. Right. So and it should be in your book too. So in this case, carbon dioxide and hydrogen cyanide both form these, carbon has 2 groups around it right here. So when we're talking about Vsepr structures, it's always referenced to a central atom. So if the molecule is big enough, you can have different geometries in different positions in the molecule. Right? So we're going to keep it simple, right? So that you can recognize the central atom in there, like only 3 or 4, at most 5 members would not get too complicated. In this case, carbon's the central atom, and it has 2 groups around it. So 2 groups means linear, right? The farthest apart that these groups can get around that carbon is opposite one another. That makes the structure linear. Similarly, you got 1 group here and 1 there, 2 groups, linear. Okay. That might be one of the hardest things to do is to consider this on the same level as that. But it's important for the model that you consider groups. Actually, this is a misnomer. Valence share electron pair repulsion. The way we're designing it is it's electron group repulsion. But VSEGR apparently lost out.
I thought we counted the dots as like a pair and everything. We're counting them as well.
If they're around the central atom.
If they're around the central atom.
Yes.
Oh, okay.
Yes.
All right. Ignore all the other dots unless it's around the central atom.
Yeah, focus on the central atom. And of course, if you look over here, you can talk about the structure here, like 1, 2, 3. So the electronic structure around that oxygen would be trigonal planar. right? That's as far apart as those bonding and non-bonding electrons can get, right? So if you put these two here, those two there, and that bond over there, this forms a trigonal, an equilateral triangle.
Oh, okay.
Okay. So electronically speaking, you do have a trigonal planar electronic structure around the oxygen.
Yeah.
Yep.
But for the sake of all of our sanity, it's the geometry part of it is around the central atom.
Yeah.
Okay.
Okay, in this case, formaldehyde, right, is formed with carbon as the center, 2 hydrogens and oxygen. So we have 1, 2, 3 groups, like the discussion I just had. But this is trigonal planar. The farthest apart you can get these guys is pointing to the points of an equilateral triangle. So what's the bond angle while we're here? The internal bond angle, well, an equilateral triangle, what do the angles have to add up to? 180, right? Okay.
Yeah.
So each one of these would be 60 degrees. But if you're looking at a center to that point, what's the angle on that one? Right? If you go all the way around, it's got to be 360, doesn't it? So each one of these has to be 120. So the actual bond angle here is 120 degrees. Okay. Everybody had geometry? Okay, the authors here like to call this angular. I like bent. Bent's more descriptive. Angular could be anything. Bent means that it used to be straight, we just get like that. The electronic structure here is trigonal planar, right? But if you cover this one up, then you're left with bent. Okay. Now, what would be the bond angle? Well, theoretically, this bond angle would be like that one, 120. Right? In reality, though, since these electrons are not bonded to anything, they're not confined between 2 atoms. They're just hanging out there. They tend to balloon, right? So their charge distributes out further and puts pressure on these bonds to squeeze. So in reality, the bond angle here is less than 120. I can't tell you exactly what it is. It might be 108 or 110 or even 115 or something like that. But it's less than 120 because of this ballooning here. Okay, so if you have 4 groups, the electronic structure is going to be tetrahedral. Tetrahedral, tetrahedral, tetrahedral. But if we have lone pairs, in this one, that's methane, right? That's natural gas. And in this one, I showed you earlier, is trigonal pyramid, or ammonia, because you have this one lone pair up here. And then for water, it's bent, because you have 2 lone pairs. Okay? This just makes the point that you can consider the geometry around different atoms in a molecule. As it turns out, if the molecule is completely symmetrical, like acetylene, this carbon is exactly bonded the same way as this one is. So this is linear and that's linear. So if they're both linear, then the whole molecule has to be linear. Whereas this one hydrogen peroxide, if you just look at this section right here, that's going to be bent on this side. And on this side, it's going to be bent the other direction. So it's actually going to look like this. Hydrogen peroxide. With that. So it's going to have two bends in it. Bent this way and bent this way.
Because of how the electrons pull it. And they're trying to get away from each other. So
they try to get as far apart, yeah. It wouldn't make sense to put these two on that side and bend it this way. That would be higher energy.
Yeah.
Now, arguments can be made that at some point they transition through those steps, but they don't stay there. And then hydrogen azide, right, has 3 nitrogens and 1 hydrogen. So around this one, you've got 1, 2, 3 groups, which means trigonal planar, electronic. And since that one is a lone pair, this one will be bent. This one is a double, so there are 2 pairs, makes it linear around this nitrogen, and there are no lone pairs, so it's linear molecular as well. So this one's bent, and this one's linear. So those are 2 different geometric centers, we call them, in a molecule. Okay, and this is extended explanation for what we just saw. Actually, that's not drawn correctly. These 2 ought to be over here. That one ought to be over here. Okay. I don't know if I took this out of your book or my book. I think I took it out of mine. But if we consider the number of electron pairs, or I like electron groups in this column, and then the electronic geometry here, then we can have 2 groups. If you only have 1 group, then you really don't have any geometry. So you have to have at least 2. 2 groups. You could have 3 groups, 4, 5, and we'll stop at 6. So if you have 2 groups, the electronic structure is linear. Okay. And a good example of that is carbon dioxide, which would be if you have 3 groups, then you're talking about Trigonal Planar. That just means it's a triangle in one plane, which means an equilateral triangle. And a good example of that is, let's see. Boron trihydride. Notice that hydrogen has duets. The boron's only got 6 electrons. It doesn't have an octet. Well, let's see if we've used up all our electrons while we're here. See, boron is 1, 2, 3. It has 3 electrons. 3, 4, 5, 6. So 6 total electrons, 2, 4, 6. They're all used up. That brings up another point. Theories or models are designed to explain reality, not the other way around. Right? We don't bend reality to accommodate our models. So we know that boron trihydride exists. So if our model is going to fit the reality, then we have to make an exception rule. Sometimes you don't make an octet. And boron is an example of that. Sometimes you exceed the octet. And usually when that happens, you're getting down into this area here, definitely down here. Because this is the third period, which means what? 3s, 3p, 3d. You have access to d orbitals now. So rather than going 2 for s's and 6 for p's, you might have room for d electrons in there for your geometry. So you can exceed an octet. Okay, back to this one. So with 4, remember that's a tetrahedron. You have 4 groups, tetrahedron, and a good example of that is methane. Right? If you have 5 groups, the most efficient arrangement is to put 2 up here and 3 around this axis. That puts them as far apart from each other as possible. And that's called a trigonal bipyramid. Okay. What examples? My mind's gone blank. Maybe one will come up. And then if you have 6, that's an octahedron, in which you have 2 up here and then 4 positioned in a square around the center. Now, if all of these positions of these geometric structures are occupied by atoms, then the electronic geometry and the molecular geometry are identical. And the examples I've given here are just that. These are all filled. These electron groups are part of bonding pairs. If, however, you have a situation, for instance, let's see, if we have a tetrahedral shape, and now one of them is a non-bonding, then what's left over for molecular is a trigonal pyramid, like ammonia. Or if 2 of them are non-bonding, you have a bent molecule, like water. If we start with a trigonal bipyramid here with 5 groups, and one of them is a non-bonding pair, the most efficient arrangement there is to put that non-bonding pair down here in the plane, in this trigonal plane. And then the molecular model becomes a seesaw. So if you take that, just turn it on its side, you see you got the legs here and the seesaw. That's the most efficient way to accommodate the electron density around here with the least repulsion. If 2 of them are missing, then you have a T-shape. You put these 2 pairs still in the plane here. Now you have a T-shape geometric form. And if you have 3 non-bonding pairs in this arrangement, then you back to a linear. That question?
Yeah, would those be bent? Because
Where?
the linear one, because it has the 2 empty shells pretty much on the one side and only one on the other. Would be like
Well, okay, this one is occupied, that one's occupied.
Yeah.
But these guys are in the center.
Yeah.
So they're pushing equally against this one and against that one. And they keep them separated far apart.
Oh, okay.
That makes them linear.
Yeah.
let's see. I would have to run out of room. Maybe I'll just write on the board over here. Let's determine the shape of each of the following molecules and see if we can figure the bond angles. So HCN. So we got 1 electron here, 4 there is 5, 5 here is 10, right? 10 electrons. So carbon in the center. Okay, so that's 2, 4. Leaves us 6. So we work from the outside in. So 2, 4, 6. Okay, all of our electrons now are used up. Now we have to, if at all possible, make duets and octets. Okay, hydrogen's covered. So how are we going to make an octet? This one's already got an octet, but carbon needs one. So we're going to take these two, make a bond. These two, make a bond. So nitrogen still thinks it has an octet, but now carbon thinks it has an octet. Right. So if we redraw that, 2, 4, 6, 8, 10. 2, 4, 6, 10. We're good. So now we look at, we've got the Lewis structure. We look at the central atom. It has 2 groups, so it's linear. Right? And there are no lone pairs around the central atom, so the geometry is linear. I mean, the molecular geometry is linear. Okay? So now what's the bond angle around the central atom? 180 degrees. Right? Oops. Give away the answer. Back up, back up. It's that one. We did ammonia before. Remember, ammonia turned out to be like this. Trigonal pyramid, and the bond angles would be, well, in a tetrahedron, the bond angles are 109.5 degrees. So the bond angle from, we go here, here like that. That's 109 degrees. But it's going to be less than. This is theoretical for a tetrahedron. But since we got this ballooning pair up here, it's going to be less than 109, maybe 105 or something like that. But if the question is asked on a test, I know that's what you're wondering. 109.5. The rest of them are logical. I mean, you can figure it from your experience with geometry. But this one is a little more difficult to do, so just memorize that one. The bond angles in a tetrahedron with the central atom are 109.5. Okay. Now, ozone. How do we do ozone? Well, O3, we have 6 electrons each, so that's 18 electrons total. And we bond there, so that's 4. 14 electrons. Start from the outside in. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Got 2 electrons left. So those will have to go in here. Okay. So these 2 have octets, that one doesn't. So how are we going to make an octet here? We scavenge a couple from one of either side, right? Like that. So now we've got this, that, and that. It didn't make any sense to take this pair and put it into a bond because that wouldn't help this oxygen at all. It would still only have 6. So we have to take a pair from the outside to bring it in. So that means 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Notice that this is one of those examples where you could easily write a Lewis structure by taking a pair from the other side. So we have that resonance thing again. But if we're settled on this structure here, there, then we look at around the central atom, we have 1, 2, 3 groups, which means trigonal planar, right? Electronic, but there's a lone pair, so it has to be bent. All right, so trigonal planar establishes the bond angle at 120 degrees. Right? Right, so there's linear for this one, 120 for that one. Trigonal pyramid, they're saying that the bond is 107. That's because of that ballooning effect. So normally the tetrahedral angle would be 109.5, but we've got a trigonal planar molecular geometry with that lone pair up there ballooned out, pushing down and decreasing the angle from 109.5 to 107. On a test, I would accept 109.5, unless the question were specifically something like, let's say, is it equal to, less than, or greater than 109.5? And you would look at that ballooning and say, well, less than 109.5. It's pushing on. Let's see, I want to get done by 11, so we got time for our lab. Yeah, bleed over into next. I hope we don't have to. Let's see how far we can get along. Which theory predicts the molecular geometry of a molecule? The Vsepr. Okay, electronegativity. I've been alluding to electronegativity up to this point by calling it an attraction by the atom for electrons. And that's what we mean by electronegativity. The more electronegative an atom is, the stronger it pulls on electrons around it. So if two atoms, two different elements, atoms of different elements, approach each other to bond, and they're not the same, I said that different, they're different, then one of them is going to attract electrons more strongly than the other. It may not be strongly enough to form an ionic bond. Right? If one is a metal, one is a non-metal, then one will win and attract electrons, and the other one will lose. But if they're both non-metals, then you can still have a slight difference in electronegativity or the pull on electrons. And that's where the polarity of the bonds come from. The one that pulls the strongest gets the slight negative charge. So there are trends in the periodic table that can help inform whether or not one is more electronegative than the other. Okay? And to begin with, we look at groups, right? So if you're within a group, which is more electronegative? Up in period, like, which is true. The higher up, the more electronegative. Okay, so if it's above, if you're in the same group, and this one's above the other one, it's more electronegative than the one below it. If you're in a period, like that, then the one to the right is more electronegative. Okay? So that means when you combine those two over the whole table, lower left to upper right, increasing electronegativity. So the lowest electronegativity is way down there in the lower left-hand corner. And the highest electronegativity, or the strongest attraction to electrons, is way up here, fluorine. These guys don't count. We don't even consider noble gases in this calculation. So it increases from lower left to upper right. And in fact, the Pauling scale, developed by Linus Pauling, places 4.0 as the value for electronegativity, strongest. And then cesium, I think, is down around, I don't know, 0.3 or 0.4, something like that. It's pretty low. And that begs the question, well, what are those numbers good for? Well, if you get two atoms together and you know what their electronegativities are, then you subtract the little one from the big one and find out just how ionic the character is for that bond, right? If the values are very far apart, like 0.5 from 4 would be 3.5. 3.5 is a huge number. That is 100% ionic. Right? But if you subtract the two and you get something in the neighborhood of maybe 2, then it has a substantial substantial covalent character, excuse me. And let's see, they only give us rubidium. That's okay. So as you go up, more electronegative here, more electronegative. And these examples are taken from the representative elements. That is from these two and these 6 here. Well, not counting those. Those are the representative elements. And we use those because they tend to fit the model better. Once you start getting into here, into the transition metals, then things sort of go like this, and then they go like that, and then they go back up like that. So it's not as pretty a story. So the trend, from bottom to top, you have an increasing electronegativity. From left to right, you have an increase in electronegativity. So low down here, high up here. Okay, so what's the explanation for why, when you go from left to right, why do you have an increase in electronegativity? Well, within a period, you're in that same energy level, right? So you're adding electrons in the same energy level, but what are you also doing? You're adding protons. And the electron energy level is based upon how far it is from the nucleus. So if it's in one energy level here, you're not adding energy, electrons closer or farther away from the nucleus on average. But you are adding a lot of extra positive charge to the nucleus, which makes a stronger attraction. So as you go from left to right, the increase in electronegativity is due to the effective nuclear charge. You're increasing the number of protons. Now, how about from top to bottom? Well, what are we doing as we go from here to here? We're adding energy levels. So you're building out. Even though you're adding protons, you're increasing the atomic size. And what that does is, as you're adding these extra electrons out here, in addition to the protons, what you're doing is adding shielding. The core electrons are building up inside, and they're shielding that positive charge that you're adding in the nucleus from being felt in the outer regions. So we're adding electrons, yes, but we're adding way, way, way farther from the nucleus, so they just don't feel the charge. And so as you add them here, as you go down, these valence electrons out there don't feel the positive charge as much. So the electronegativity decreases. Okay, so let's take an example. If we get lithium and fluorine reacting, which element will have more attraction for an electron? Let's see where they are. Let's see. Fluorine and lithium. Okay, they're in the same period, so we can use the left to right rule. So fluorine is going to be the more electronegative. That means it's going to have the stronger attraction.
Can I just automatically say fluorine because it's at the very top of the list? Fluorine and
Yeah, because there's no competition for fluorine, right? Yeah, oh yeah.
I read that question, I was like, wait a minute.
There's a trick here. Yeah. Okay. In a bond between fluorine and iodine, so they're both halogens, they're in the same answer, right? Fluorine is higher up than iodine, so it's a stronger attraction. But if we said iodine and chlorine, then you would say, okay, chlorine's above iodine. And there are compounds, lots of compounds that have been studied. They're formed only from halogens. Okay. Which of the following elements has the highest electronegativity? Well, let's see.
Really don't count.
It doesn't count.
You don't count.
Right? So we have to say hydrogen, oxygen, chlorine. So here's oxygen. There's hydrogen. There's chlorine.
Oxygen? It's
Oh,
higher
excuse
than
me,
chlorine?
oxygen and chlorine. It's higher than, but it's to the left of. That's a difficult question, right? Because you've got two things operating here, and they're in competition. So which one wins out? Well, let's see. Oxygen is above chlorine.
It'd have less electrons overall, wouldn't it?
Yeah.
That's kind of what I'm going
It'd have less shielding. So I think you're right. Oxygen is probably.
Finally, I'm starting to put something together.
Yeah, I think oxygen is correct.
You know, these last two questions don't make a lot of sense when you really get down to it. Fluorine versus, you know, what other competition? And then two that could essentially be the same.
Right. The only way to be absolutely certain is quantitative. You know, look at the numbers. We're trying to make educated guesses at this point. So now to the back to the topic of bond polarity. If one is stronger than the other in an electron attraction, it creates a polar bond. And we designate that polarity with an arrow with a plus. So that's the plus end, this is the negative end. And that's assigned to a bond between two atoms. So it'll be, if this one's more electronegative, it'll be like that. And that's known as a dipole. There we go. Now, obviously, if you have the same element bonded to another element, bonded to one of its own kind, that's nonpolar. There's no other substitute. That has to be. If the bonds are covalent, but one of them is a stronger attractant, we call it a polar covalent bond. And hydrogen sort of fits in there because it's off here by itself. But when it's bonded to a nonmetal, it forms a covalent bond. If it's bonded to a metal, then it'll form an ionic bond. I think I mentioned that last time, the hydrides are like that. So this is the way we represent the dipole. And in one way we do it this way. In another way, we use that small delta Greek delta with a sign to show the slight difference in charge. Either way is acceptable. Now, how do we differentiate between full ionic, nonpolar covalent, and in between? Well, if we have access to the electronegativities and you subtract the smaller from the larger, then that number gives us some semi-quantitative indication as to where the breaking point is. And roughly speaking, if the difference is 0.4 or less, we consider it nonpolar covalent. So you can have two different elements bound together. If the difference in their electronegativities is 0.4 or less, we're going to call it nonpolar covalent. If it's between 1.5 and 0.4, we call it polar covalent. Actually, between 0.4 and 2, you can get polar covalent. But there is potential for a significant ionic character above 1.5. If both, okay, here's the stipulation. If a metal is present and you see these differences, anything above 1.5, if a metal is present in there, then it's going to be ionic. But if both of them are nonmetals and it still hadn't reached 2.0, then it's still polar covalent. Right? So that's kind of a little trick. Anything above 2, it doesn't matter what the atoms are. Anything above 2 difference is ionic in character. Okay. Arrange the following bonds in the descending order of polarity. That is, the most polar to the left and the least polar to the right. So this one should be easy because fluorine's there, right? So they're all going to be polar bonds. Which ones have the greatest separation will be the most polar. So let's see, fluorine looks like nitrogen's furthest to the left. No, carbon. So it should be CF first, then NF, then OF. Now, if we have CF here, okay, that's pretty far apart. NO, that's very close together. And silicon fluorine. Okay, I would say that silicon and fluorine, because it's not only to the left but below, silicon and fluorine would be the most polar. Then carbon and fluorine would be the next, followed by NO, would be the least polar. This one would be the least polar because they're both identical, right? So that'd be the last one. Then we just need to decide between boron and sulfur and chlorine. So boron's over here, sulfur's over there. I'd say boron and chlorine first, then sulfur and chlorine, and then chlorine. Which one of the following bonds would be the least polar, yet still be considered polar covalent? All right, so let's read this question backwards. It has to be covalent, right? So we can't have metals. Okay, silicon's still okay. All right, so the rest are covalent, but which is polar? Can't be this one, right? Eliminate those two. Now we only have 3 to deal with. So which would be the least polar? The ones that are closest together in their position on the chart. So there's carbon and oxygen, pretty close together. Silicon and oxygen, that's farther apart. Nitrogen and oxygen, they're the closest together.
So, CO.
It's just asking for the least.
Oh, just the least.
Yeah. And still be polar covalent. That's why we had to eliminate this one and this one first, because it didn't satisfy that condition.
One was covalent and the other wasn't polar.
Right.
Yeah.
Exactly. Okay. Which of the following would be the most polar without being considered ionic? Okay. Without being considered ionic. Okay, so we got that one out. The most polar. That's the same group, isn't it?
Yeah.
So we just need the farthest apart. This one.
Yeah. Can the next test just be all like questions like this? Is this right so far as like,
Makes sense.
oh yeah, this makes the most sense out of everything. Easiest to pick up, easiest to apply.
Polar covalent compound is a, let's see, which statement? Polar covalent bond. Unequal sharing of electrons between two atoms. It's still sharing, but it's unequal. So molecular polarity. I guess I kind of jumped the gun earlier. The molecular polarity is a consequence of polar bonds plus an asymmetric molecule. If you have polar bonds that don't cancel one another out in a regular geometry, then you have the potential for a polar molecule. It's unsymmetrical distribution of electron charge. So you have to consider both of these two. The individual bond polarities plus the molecular geometry. For instance, that's a polar bond, right? But they're facing opposite one another because of the linear structure of carbon dioxide. They cancel one another out. So carbon dioxide is nonpolar. This polarity for hydrogen cyanide is toward carbon for this bond and toward nitrogen for that bond. So overall, even though it's symmetrical, the bonds reinforce one another. The polarities reinforce. So this is a polar molecule. This one's polar because it's bent, right? They have opposite dipoles, but their vector sum. You ever heard that term? There's arithmetic sum, which is 1 + 1 = 2. But vector sum takes into account geometry. So if you have, in physics, if you say there's a fixed point here and you've got a force being pulled like this and a force being pulled like that, those two forces together, when you add them up, that's the vector sum. So the vector sum of this one would be added up in that direction. So that makes it a polar molecule. Based upon the dipoles of the bond plus its geometry. True or false? Molecule that has polar bonds will always be polar. It's not a trick question. Is it true? If they have polar bonds, the molecule will always be polar. Depends on the geometry, right? If those polar bonds are positioned so they cancel one another out, you have a nonpolar molecule. Okay. How we doing? This one. I don't want to run out of time. Let's get that one too. Let's see. Okay. Did I give you type 1, type 2, type 3 compound naming already? Good. Good. Oh, yeah. I'll run over it real quick. Okay. Type 1 compound, type 2 compound, type 3. And this is with respect to naming conventions, right? A type 1 compound is formed from a metal and a nonmetal. A type 2 compound is also formed from a metal and a nonmetal. A type 3 is always from a nonmetal and a nonmetal. Okay? So, if you want to know which rules apply, you ask yourself, is it a metal nonmetal? Right? If it's non-metal nonmetal, go straight there. If it's a metal nonmetal, you go to one of these. Then you have to differentiate between these two. Okay? In this case, the metal is a fixed charge. And those always come from alkaline metals, alkaline earths, or the boron group. Okay? That's the only ones you have to worry about. Fixed charge metal. This one is variable charge. That's everybody else. All the transition metals, well, with the exception of zinc and silver. But like I said before, for simplicity's sake, you can treat zinc and silver as if they're type 2 if you want. So, now that you've got that picture, if a metal happens to be fixed charge, then all you have to do is put the name of the metal, for instance, this one, just name the metal, and then change the second one, the anion, to an IDE, sodium chloride. You don't have to say how many there are. You don't have to say what the charge is, because the charge is fixed. And the ratio between sodium and chloride will always be the same, 1 to 1, because this is 1, that's 1. How do you know those charges? All these are plus 1s, all these are plus 2s, all these are plus 3s, all these are minus 1, minus 2, minus 3. Okay? Variable charge. If we have something like this, Fe2O3, you look for iron. Iron is here. So it's a transition metal. It can have variable charge. Now what you have to do is decide what is the charge, right? Oxygen is always 2 minus. So that's 6 minus total. 3 times 2 minus. So that means these two irons have to balance that 6 minus with a 6 plus total. How do you get 6 plus total out of 2 irons? Each one has to be 3 plus. Then you name it. Iron with its charge, oxide. That's the difference between these and these. You always have to say what the charge is. Now, if you have polyatomic ion, it can fit in either one of these, depending on what metal it's bound to. So if you have sulfate or phosphate or something like that, then the polyatomic will just behave with its name. You don't have to change its name. It has a fixed charge. It has a name, like sulfate is different than sulfite, and just balance the charge. Okay, so now to type 3s, non-metal, non-metal. We follow the binary ionic model for naming non-metal, non-metals, but they are not ionic. They are covalently bound, but we use the model to name them. We just modify the model so that we say exactly how many atoms of each element are in the compound. So if we say this one, N2O5, we use the Greek prefix for the 2 and the Greek prefix for the 5. So we say di, nitrogen, penta, oxide, or pentoxide actually is better. That's all there is to it. You just say how many there are. Now the rules are written to be unambiguous. That's the key word. Which means when you see this, that's the only way to write it. There's no other way. And the reason it needs to be that way is because if you see this, you can write that from the name. If it's ambiguous, you could write 2 or 3 or 4 different types. And then the nomenclature rules would be worthless. Like, it has to be unambiguous. That's why they're constructed this way. So your decision tree is when you see a compound, either name or a formula, you ask yourself first, metal, nonmetal, or non-metal, nonmetal. So that puts it either over here or over there. If it's over here, you say fixed or variable. Then you go to whichever step works. Okay, there are the prefixes. So prefix for 1 is mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. And examples. You need to memorize those if you don't already know them. Now, one exception. If you only have 1 in the first position, you don't say mono. If it's just 1 nitrogen, you just say nitrogen. Dioxide. Okay? You only say mono if it's in the second one. And that extra credit handout I gave you for naming 50 ways to name your compound, that's supposed to help you reinforce the rules. Oh, the one thing, there are some in there that we haven't talked about. What do you do when it says something like pentahydrate? So we have copper, let's see, copper 2, sulfate, pentahydrate. How do we write that? Well, copper is going to have a 2+ charge. Sulfate is going to have a 2- charge, so there's a balance. Then you got this pentahydrate hanging out here. What does that mean? This is water of hydration. We put a dot, not down on the line, not up here, right in the middle. And then we add the number of waters that are attached to it, like that. So if it says something hydrate, you put how many of those waters are attached, just like that. Okay? Or if you see it like this, then you name this first, and then you say how many of these waters there are.
It's okay. All balanced, right?
Yeah, this is the balancing part. These are just kind of hangers on. That's why they're separated by that dot. Yeah, they don't enter into the charge balance. Do this first, then you add those. Okay?
Yeah, I'm just trying to figure out why someone would write it like that and make it so complicated when all they got to do is, like, separate it.
Well, like I said before, these naming conventions, the theories and the rules have to be written to accommodate reality. And this is reality. If you take copper sulfate isolated in a solution, it's going to be a pretty blue. You dry it down, but you only dry it down at 100 degrees, which would be the normal boiling point of water. It'll drive off most of the water, but it's going to leave some water behind. Not warm enough to remove. Those are the waters that are stuck in the crystal structure, bound more tightly. You can remove them if you heat it up to about 120 to 130 degrees. And we know that because you can weigh it, then you can heat it up, weigh it again, and find out what was driven off. And you can determine the ratio, the molar ratio of this to the whole. In fact, I just did that with my general chemistry class yesterday. They did that very experiment. Now we'll see whether they understand it when they turn in their reports. Okay. Some things have common names, like water. I read this paper. Somebody thought he was being smart. He wrote this toxicity paper. And he or she, I don't remember who, titled it, The Toxicity of Dihydrogen Oxide. We're talking about water. Hydrogen peroxide, ammonia, special name, hydrazine, methane. These are organic compounds, and there's a complete set of nomenclatures for organic compounds. So that's where these two are leading: methane, ethane, propane, butane. This whole set of nomenclatures for organics that we're not going to cover. Penta means 5. Okay. And then we have concept questions. We really don't have time for that because we got to get in the lab. Okay, take a short break and we'll reconvene in the lab and do our binary separation. Shut this down. We're finished here.